Okay, let's look at some properties of complex numbers. Now, what they mention is, I think they say it's a field. Maybe they don't say that up there. Oh, no, in the proposition they say it's a field. So a field is a particular number structure, algebraic structure. If you take our abstract algebra course, you learn about fields. But a field is really just a set of numbers that has, for one, both an addition and a multiplication. Now, it also has to have an identity, both additive and multiplicative identities. So we have, for instance, let's see. So, well, we'll list some of their properties. They list a property 1.4, and that is closure under addition. Okay, that's to say if I take two complex numbers and add them using that definition of addition, I get another complex number. Well, certainly, because remember, a complex number is simply an ordered pair like this, or like this in AB. So if they're elements of the complex numbers, then it says so is the addition. So, x, y plus AB is also an element of the complex numbers. And now the idea to prove this, well, you have to use the definition. And so what we know is that to be a complex number, I have to write it as an ordered pair where each element of the ordered pair is a real number. Okay, so what we have, if you want to look at a proof of something like this, so xy and AB, elements of complex numbers, well, that implies that x, y, a, b are all elements of the real numbers. Okay, so those are all elements of the real numbers, and so now when we add them, so xy plus ab is equal to x plus a, comma, y plus b. Okay, but x plus a is an element of the real numbers, since x and a are elements of the real numbers. So we already know, we know that if we add two real numbers, we get a real number. And y plus b is an element of the real numbers, since y and b are elements of the real numbers. And so x plus a, y plus b is just an ordered pair where those are both real, and so it's an element of the complex numbers. So it's not a real deep sort of proof here or anything like that, but that's the idea of these proofs, is they typically go back to just this definition of what a complex number is, and then properties of real numbers. So we already know the properties of real numbers. Now 1.5, that property they have listed is that the associative property. Okay, so associative property. Property. Okay, of addition. So that's what we're looking at there. And you know, so what it's just saying that if I were to take x y plus AB and add those first, then add to that the result of CD, then that's the same thing as if I had actually added the AB to the CD first and then added the XY. So that's the associative property of addition. 1.6 is commutative property of addition. Okay, property of addition. So, you know, these are things that you're used to with real numbers, and they work with complex numbers. The commutative property of addition says, oh, well, if I take x, y, and I add to that AB, then, well, I could have thought of it as AB plus XY. So there's our commutative property. 1.7 is 0, 0 is the additive, oops, two D's there. Oops, try that again. Okay, additive identity. Okay, so that's just saying that if I take you know, xy plus 0, 0, I get back xy. And of course, I could do that as 0, 0 plus xy because we know addition commutes. Property 1.8 tells us we have additive inverses. And again, these are things that you would hope we would have. But, you know, pretty much we have to show all these are true in order to say we really do have a field. Okay, so these are just the properties of a field. And so we have additive inverses, and so that is that if we take x and y, the real numbers xy, and we add to those the real numbers negative x, negative y, we'll get the additive identity element 0, 0. Okay. 1.9. In this case, this is our distributive property. Okay, distributive property of multiplication, there we go, over addition. Okay, so if I take my xy and I multiply that by, or multiply the sum of AB plus CD, that again, just like with real numbers, I could have done xy times AB plus xy times CD. So we've got that. Then property 110. By the way, the textbook proves 1.8. Then 110. 110 is closure under multiplication. Okay, so that's to say that that our xy times AB is indeed an element of the complex numbers. So once again, if I were to do this proof, we'll do another closure proof here. This one being a bit nastier to deal with, but it's really the same idea. Sorry, I keep bouncing this thing around. So, we have that xy and AB are elements of the complex numbers. Well, so again, x, y, a, and b are elements of the real numbers. Okay, now we do our multiplication. Got xy times ab, and that multiplication is xa minus yb, and then xb plus ya. Okay, but xa minus yb is an element of the real numbers, and xb plus ya is an element of the real numbers. And so xa minus yb, xb plus ya is an element of the complex numbers. Okay, so again, it just appeals to that definition of what a complex number is, but a complex number is just an ordered pair of real numbers. Okay, so that was 110. Then 111, associativity of multiplication. Okay, so what I'm doing is I'm making sure you realize the names of these things. So again, that's the idea that if we take xy times AB, and we do that first and then multiply by CD, that we could have just as well first multiplied AB and CD, and then taken that result and multiplied it by XY. 112, multiplication commutes. Okay. So multiplication is commutative. And so there we're just saying, hey, if I've got XY times AB, that's the same as AB times XY. 113, 10 is the multiplicative identity. Okay, so that's to say if we take XY times 10, we get XY. And, you know, here the proof, I'll go ahead and do this proof, is just actually carrying out the multiplication. So 10, okay, by definition then that's X times 1 minus Y times 0, and then Y times 1 plus, sorry, not minus, X times 0, and so you get X, Y. So I just carried out the multiplication, and that is the proof. 114. And this one is the multiplicative inverse. Okay, multiplicative inverse. So if XY is not equal to 0, 0, then what we have is that XY times X over X squared plus Y squared, comma, minus Y over X squared plus Y squared, is equal to the multiplicative identity 1, 0. And so that's how you could do a division, is you can multiply by the multiplicative inverse. Okay, so there are the all the properties that they need for a field. So we have additive and multiplicative identities, additive and multiplicative inverses. Of course, no multiplicative inverse for 0. And then we have the typical associativity, commutativity, and distributive laws. So, you know, they act in that way a lot like the real numbers. And okay, so let's see if we'll finish. We'll go ahead and finish there, I guess. That's plenty.